Okay, so let's talk about what we're gonna do today. We will be finished maybe 2 slides today. Some of them we'll just go a little bit briefly. Okay, some of them we want to spend time to explain to you. So first of all, bacterial growth is binary fission. What this means is a bacteria, they have their DNA, and then they generate their daughter cells, is create a cross-wall form. And then the DNA from the mother cell and the other genetic information is exactly separated into their daughter cell. And ideally, the daughter cell should be exactly the same as a mother cell. But however, in the real life, something changed because of the mutation. This is the same, like you looks like your parents, but not the same face. It's same for the bacteria. So binary fission basically is 1 becomes 2, 2 becomes 4, and 4 becomes 8, and 8 becomes 16. So basically 2 times the power of n. So that's a basic mass. Okay, but we don't want to go that deep. They do have software talk about these. We call it a predictive microbiology, but it's a higher requirements, but not will be the scope of this class. What means the generation time? Which means how long the time required for a population to double. Which means how long it takes 1 cell become 2 cell, or obviously how long it takes 2 cell becomes 4 cell, and continues. So as we mentioned, some of the bacteria, they grow very quick. Let's say E. coli. Their generation time, 18-20 minutes. So that is why at 37 degrees Celsius, 8 hours to 10 hours, they can grow from 1 cell to 1 million cells. But some of the bacteria, they grow very slow. Mycobacteria tuberculosis, and we mentioned, if people have like a tuberculosis, you can say, I'm gonna get you sputum sample. I need to get the isolation. And then I will determine which antibiotics I need to treat you. Because it grows very slow. The doubling time is 12-24 hours. Which means 1 cell become 2 cell, it took a day. That's why for mycobacterial tuberculosis, what we need is a predetermination using acid-fast stain. That is what we talk about. If we're using acid-fast stain, we already see the presumptive purplish or like reddish colony there under the microscope. Then we will say the patient is presumptive TB. We have to do the treatment. Basically, is using antibiotics immediately. So that's a generation time. Okay, bacterial growth curve, we want to talk. Bacterial growth curve, first of all, using mass functional figure, we have x-axis is usually time. Yes, let's say seconds or hours. And the y-axis is usually the population. And basically you can say cells per ml is the concentration. Now, what the curve looks like? The curve absolutely is not like this. That's called linear. And everybody's thinking you grow a bacteria, put 1 cell, and then after a certain time it's going to grow all the way. No, it's not like that. The curve have different stage. It looks like this. At the first stage, we call lag phase, sorry. Lag phase, which means bacteria go into a medium we treat as bacteria in a new environment. He has to fit and get accustomed to the new environments. Different acid pH, different temperature. Sometimes it's harsh environments like UV lights with antimicrobials, all those things. Their lag phase is basically their preparation. Their genetic information, their metabolic processing is being ready to grow, but they're not really growing. So that's called a lag phase. At that moment, the bacterial number is basically stable. After a certain period of time, they go to a phase which is grow dramatically. We say log phase. That is what happens. 2 times the power of n. And you know that. Is that right? That equals n. So bacteria, we sometimes using log to do the expression. Because it's grow dramatically, so log phase. Now bacteria grow. They're going to using the nutrients in the bacterial media or from the environments. But at the same time, they're going through metabolic process. Like you guys learned in other classes, we have glycolysis, we have a citric acid cycle, all kinds of different metabolic cycle. Going through metabolic process, what the products they will generate is a waste or some of the toxication material. So they will reach a stage, their toxication material and the nutrients is in a balanced status. Therefore, their growing is retarded, or we say slowing down. So that moment it becomes flat. This is called stationary phase. After a certain period of time, toxication material more than nutrients, bacteria start to die. So we call death phase. That is a bacterial growth curve. Now I want to mention here several things, 2 things. So when you buy a bag of hot dog, you look at the label, you see the sodium diacetate, some chemical like potassium lactate, or sometimes citric acid. Those are antimicrobials. But you need to know antimicrobials is for inhibit bacterial growth. So we also call static. So what means inhibit? The bacteria is still there, only grows slowly. So for the inhibit, the lag phase time usually is long and delays the initiation of log phase, and also their final population little bit lower, some curve like this. That is called inhibit. Now, sometimes we also know if we are using antibiotics instead of antimicrobials, let's say we're using penicillin or amoxicillin, lots of the time bacteria will be completely died. So we say kill bacteria. We have another one called cytol, the terminology called. What this means? Which means the bacteria does not even initiate the lag phase, it starts to die like that. These are the things we want to be mentioned before we talk about the detail later on. So that's bacteria growth curve. Now, what are the factors will affect microorganism growth? Obviously, pH, temperature, water activity, and oxygen concentration. Some of these are easy. I will talk very quick, but there is one thing talk about water activity, I want to explain more. Okay, pH, everybody knows. This is simple, which means how acid it is, because minus log concentration of proton, and the range is 0 to 14, and the neutral pH is 7. For most of the bacteria, their optimal pH is around 7. Let's say our bacterial media solution, the pH is usually 6 to 7, because that is fit for most of the bacteria to grow. And you see, this is the pH range for different products. There is the chemical products, there is also the food products. So you always need to know our battery acid is very low, is 0. So that's why the old battery has to be recycled. Or you put in a bag labeled as a battery waste. You cannot just throw away in the trash can. Our stomach acid is very low. It's 1 to 2. Is that right? Neutral pH 7. And you can see some of the seawater, detergent solution, household ammonia, the pH is usually 10 to 12. That is alkaline solution. So this is everybody knows. We gotta just be quick, be little fast, okay? We could categorize bacteria based on the pH. Acidophiles, most of the time is fungi, pH 0 to 5.5. Neutrophile, that's most of the bacteria, pH range 5.5 to 8.0. Some type of the bacteria, Pseudomonas, it's a sporage bacteria, Bacillus and Micrococcus, they like alkaline environments, so pH 8 to 11.5. Majority of the bacteria, we talk about Salmonella, Campylobacter, Listeria, E. coli, they are all called neutrophile. So you can understand the most favorable pH is about 7. Okay, this is something we talk about is lower pH. Bacteria has to battle the lower pH. So what happened is that if I have a beef carcass, lots of the time we spray acid solution as antimicrobials. We just mentioned as the acid solution, it inhibits bacteria. The bacteria is still there. Those bacteria will become acid resistant. Now, acid resistant bacteria is a great challenge for food industry, because if we are going to the further cooking process, they may resistant in the high temperature. We call cross protection. That is what this slide is talking about. So for bacteria, they have their own mechanism to battle the acid environment. Lots of the times they switch with exchange with potassium and potassium or other chemicals to maintain their pH. From our perspective, we cannot stick to only one sanitizer. We need to use different to do the rotation to avoid acid resistant. But honestly, we cannot completely avoid that. We can eliminate or limit the cross protection impacts. Okay, so that's a pH. Temperature. Why temperature is important? Because temperature, same for bacteria, same as a human being. We have an optimal temperature range. So most of the time we are comfortable 37 degrees Celsius. If your temperature is more, human body temperature more than 38.5 or 100.4 degrees Fahrenheit, you have a fever. And you feel very uncomfortable because your metabolic processing is disturbed. Same as the bacteria. The bacteria, they all have a minimal optimal and maximal temperature range. So, based on their temperature requirements, we could categorize bacteria in different range and different name. So let's look at these. Some of the bacteria like very cold environments in the deep ocean. We call it psychrophiles. And those we usually say it's environmental bacteria. They have certain enzymes here can resistant or favor those very cold temperature. In our normal life, we really troubling about some of the bacteria called cyclotrophs. Why? Because cyclotrophs can grow in the refrigerator temperature. A typical example is Listeria monocytogenes. They are big risk for ham, turkey breast, hot dogs, because we always think we vacuum package, we put in the refrigerator, it's safe, but it's not because it will grow, and it can grow very well. That's why we call it cyclotrophs. Majority of the bacteria is mesophile. Salmonella, E. coli, those are mesophile. It is important they can grow on our skin surface because our skin surface is about like 25 degrees Celsius. It's well fit the range of mesophile. Now heating basically can kill bacteria. But some of the bacteria, they can survive in the heat environment. We call them thermophiles. Which bacteria? Bacillus. They like heat environments. Could be up to 60, 70 degrees Celsius. They are one type of the bacteria can survive in much higher temperature. We call hyperthermophiles. Again, those are environmental bacteria. Where you can see hyperthermophile? Did you ever go Yellowstone National Park in Wyoming? In the hot springs, those bacteria are usually highly heat resistant. We call them hyperthermophiles. They are one bacteria some of you heard about, some of you learned in your other classes, but you did not realize it's a hyperthermophile. Did you ever do the research with other faculty about or heard about PCR? Polymerase chain reaction? You heard about that? During the PCR processing, we had the enzyme called TAC enzyme. Okay, where the TAC enzyme comes from? Comes from a bacteria called Geobacillus. Because the PCR processing have a thermal processing, the temperature 94 degrees Celsius, they have to be survived. Geobacillus is a place where TAC enzyme is isolated. And Geobacillus can survive up to 110 degrees Celsius. So it is a quality control species for our autoclave machine. So you know everything put in the autoclave room, after 15 minutes should be all cured ideally. Because we're using Geobacillus as a thermophile, hyperthermophile to do the quality control. Which being said, if after autoclave the Geobacillus is still survive, then the autoclave machine needs to be fixing because it's failed. Okay, so that's what's the temperature for categorizing of the bacteria. This is a range. Well, major students need to remember, you don't have to. If I ask you, you can find it. Okay? You don't have to remember the range. Our major students need to remember the range for these. But like I said, most of the bacteria is 20 to 45 degrees Celsius. That's called mesophile. Basically in the lab, 35, 37 degrees Celsius incubator. Water activity. Okay, this is something we will spending maybe 20 minutes to talk about this. This is the most tricky question for people to understand, and I want to explain very well to you because you can know what this means. So this concept, because it has water there, so it's very confusing. Okay, first of all, water activity does not mean moisture content. So a couple of years ago, when I asked even my graduate students, a major student, I said, what is water activity? Because we have a machine. The machine is expensive, $20,000. And we had a chicken breast. We're using antimicrobials. And then we cut into small pieces. We put in the machine. We're testing water activity. And it reads like 0.994. I'll tell you why the number is like that. Then I asked my students, I said, what is the water activity? She doesn't even think it. She said, that's amount of the water in the food. No, that is called moisture content. So moisture content is the amount of the water in a food. That's called moisture content. That is not water activity. So what is water activity? Water activity are using AW. Okay? Well, I need to draw here. That equals partial vapor pressure above a food product divided by partial vapor pressure of a pure water. This sounds very tricky, like a complicated physics and a math question, and a math formula. What this means? How much space we have? Okay. We want to explain to you what this means. Okay? Okay, I had a closed vessel. I put a water there. Okay, what is water molecule looks like? H2O. That's water. Lots of water. Okay. Water molecule looks like this. So you have. So chemistry, you know, this is called covalent bond. This is called hydrogen bond. This angle is 109.5 degrees. That's what a water molecule always moving, always jumping around. If in the closed vessel we have a bottle, we have a water molecule there. They were jumping around. Some of them go out, some of them comes back. Lots of them come do like this. And at the end of the day, with a set up temperature, they will reach an equilibrium status. Then generate a pressure here. This is called vapor pressure. Now, why I say is if affected by temperature. So what happened is, if I'm doing heating here, what's going to happen? The vibration will happen. So the vapor pressure will be increased. If the vapor pressure equals atmosphere temperature, atmosphere pressure, we usually call like 1 standard Pascal. What will happen? I heat it, then the vapor pressure increased. At some point, equal atmosphere pressure. So what will happen is boiling. Is that right? That's what we call it boiling. So that's what is a vapor pressure. Now, of course, you know, goes this way. The boiling temperature. This is elevation. This is usually is at we should go boiling temperature. So sorry, we should go different way. Sorry, we should go a different way. We got this one. Okay, this is the boiling temperature. This is the elevation. So at sea level, this is sea level, 100 degrees Celsius boiling. In the highest mountain in the world, in Everest, in Nepal, how many? 70 degrees Celsius. Our water will be boiled. So from the food safety standpoint, you cook an egg at 70 degrees Celsius, start to boil. But not means it's going to well cooked. How about West Virginia? We are in Appalachian Mountain. Our boiling temperature is around 94 degrees Celsius. And you can do a testing. I tested in the lab. It's not 100. So let's say Rocky Mountain at Colorado and Wyoming area. The boiling temperature is usually about 91 degrees Celsius. So just want to let you know that what happened. Okay, that is called vapor pressure. Vapor pressure for pure water, we always set 1.00. Now, what means a food? Now the food product, of course it has water. Every food product has water. But more important, what they have other nutrients. They have protein, they have salt, they have sugar, we call it carbohydrates, and fatty acids, all kinds of things. Once you have those macromolecular, they're going to drag in down the water molecule. So let's say water molecule are going to go out. Water molecule are going to go out. Going to go out. They will push them back. Push them back. What this means? The vapor pressure will decrease. Will decrease. So water activity is actually a comparison ratio. That's why it ranges from 0 to 1.000. So some of the products is really high water activity. For example, hot dog, 0.996. How about beef jerky? Dry, 0.900. How about chips? Low. Chips is about 0.25. How about the milk powder? You like milk powder? You can have made the milk 0.50. So what does this really mean? available water to be used by bacteria. That's why it says index of available water. Okay? Available water to be used by bacteria. Now, you said this, water activity and the moisture content are not equal. But how come you said hot dog, you said maybe vegetables is a higher amount of the water, higher amount of the moisture content, but also water activity is high? Why? Because there is a very important curve comes out. X-axis is moisture content. We call equilibrium moisture content. Y-axis is water activity. Long time ago, the food scientists and the microbiologists and the food chemists, they worked together. They're using starch as a sample to do the absorption and desorption curve, what it looks like. So what this means, if I have a starch sample in a closed chamber, and I put sodium chloride or calcium chloride there, then after a certain period of time, I take the sample, I go ahead to weight. I measure moisture content, I also measure water activity. I get that curve. And then I separate them into different range. The first range is about 0.25. Second, 0.25 to 0.50. The last one, we all the way go to 0.95. We basically separate them into small section. This is, we call it a mono layer. This is additional layer. And this is capillary water. In different segments, we have different food. That's why we say living in a microbiology world. In here, what are the examples? Chips. So, very simple. Did you ever heard about, there is a news report said, today we had 5,000 pounds of chips is recalled because E. coli 0157H7 outbreaks. You never heard about that. Because this area, we don't worry about bacterial contamination. It's not a favorable water activity and moisture content for bacteria to grow. But what we care about, chips, if you open a bag, left on your dorm for about 7 days, you go back to taste it, it becomes soft and a little bit like a sweet flavor. Why? Because it's going through lipids oxidation. And we call rancidity. We don't like that. So at this curve, there is something happened like this. This is lipids oxidation. So we don't want to go detail about here. Okay, that's microbiology class, that's chemistry. Second category. Do you like chewy chocolate bar? It's too much sugar, but some people like it. You like milk powder? Lots of you. Did you ever hear about chocolate bar have outbreaks? Barely, not really often, not on the news. Because in this area also, not much for pathogen grow. Maybe fungi. But what we care about, ingredients. Let's say milk powder. Did you ever experience milk powder becomes yellow? Chemical spoilage. Why? Maillard reaction. That's what we're going to talk. Not today, in the biochemistry class, not today, not in here. The curve looks like this. That's Maillard reaction. Now, what is the one where we really concerned? You hear outbreaks about beef, about vegetables, even eggs. Is that right? We have E. coli, O157H7, salmonella all the time. Why? Because they're right here. At this category, the food products is perishable. The water activity and the moisture content is almost linear. It's favor bacteria pathogen to grow. All these products, water activity is very high because available of the water to be used by bacteria is huge. So this is what happened. We talk about water activity. Now, if we want to go a little bit of detail, chips, do they have a longer shelf life? Yes. A chip bag, you can be there for a couple months, no problem. Can you do that for meat? No. So chips, longer shelf life. How about chewy chocolate bar? Intermediate, is that right? A couple of days, maybe one month, not 10 days, it's okay. Beef, very short, less than a week. What's the texture looks like? Do you like chips? Yeah, crispy very. How about chewy chocolate bar? Chewy, a moisty. How about beef vegetable? Very juicy. So that's kind of thing related to the shelf life of a bacteria for food products. Okay? So there are lots of things we can talk about is with water activity. I just want to let you know, this is a concept is a little bit tricky to understand. There is a big story behind it, but you should know, very simple, is the index of available water can be used for bacteria. And it's correlated to moisture content, but it's not the same. Okay, so that's water activity. Okay, so how we change water activity? You add salt. And you should always remember, salt, from microbiology standpoint, is not for flavor. It's not for salty. Lots of people will think about salty. Oh, I have a cucumber, it's very salty. It's not really for flavor. It will cause anosmotic balance. And salt is, we say, a natural preservatives. Based on the requirements of the salt, bacteria simply have two categories, halophile and non-halophile. Most of the bacteria are non-halophile, which means you using salt could kill them or at least inhibit. There is a one thing exception. Staphylococcus aureus. That is the reason Staphylococcus aureus can grow on our skin surface. Think about you go ahead and run a half marathon, or you play a tennis or play football. You're sweating a lot, and then a couple of hours later, you see your T-shirt have a salted marker there. Our sweat comes out with the salt. The salt is right here. This bacteria, Staphylococcus aureus, a gram-positive bacteria, can survive on the skin surface because it likes the salt. So we say it's a halophile. Another one we call it an extreme halophile. Can you guess in the United States where you can find the extreme halophile? Did you ever be in Salt Lake City in Utah? The Great Salt Lake? Huge amount of the bacteria, they're all like salt. It's extreme halophiles. So extreme halophiles, like geobacillus, like hyperthermophiles, those are usually environmental bacteria and not really existing in the lab. Okay? That's a salt. Okay, oxygen requirements. This is another relatively tricky one. So we want to talk about this. So every time when we talk about the amount of the oxygen, the requirements of the oxygen for bacteria to grow, we come out with these slides. Looks like complicated. Yes, it's very wordy. You have a picture there, you have all these things. Okay, let's put it this way to easy understand. Regardless of how complicated it is, we can categorize bacteria into three major groups, which is aerobic bacteria must use oxygen to grow. Without oxygen, they're dead. Let's say Pseudomonas. Pseudomonas fluorescens, we talked about. Pseudomonas aeruginosa, we talked about. They must have oxygen to grow. They are second group of the bacteria. Doesn't like oxygen. If they are with oxygen, they will be died. We call anaerobic bacteria. Grow without oxygen. Otherwise killed. So what are they? Clostridium. They cannot survive in the oxygen. Majority of the bacteria, it can grow with or without oxygen, but better with oxygen, and we call facultative. This is majority of the bacteria. E. coli, Salmonella, Listeria. That is why they gave us a public risk for those foodborne pathogens. Because you take out of the oxygen, it's still going to grow. That's why we call it a facultative. Majority of the bacteria in this category, especially pathogens. Then we go to see all these things. Microallophile. Microallophilic. Somewhere here. This is only grow with limited oxygen, 2 to 5%, at least less than 10% oxygen. Because oxygen for them is a toxin. Which bacteria is microallophilic? Campylobacter. This is a huge pathogen, a risk on the poultry. It's very ironic. It is microallophilic, which means you have to control the oxygen amount if you have to grow them in the lab, but it's a public health risk. It's very interesting, very ironic. And I tell you how ironic it is. On the poultry surfaces, you see the skin surfaces, it can grow very well. When you the meat of the poultry, you ground it. It's not grow very well. So it's very tough for the oxygen. Another thing, allotolerant. That's grow equally well with or without oxygen. I don't want to put it there. It's just a lower level of facultative. So, oxygen is basically like that. Now the question is, why? So why some of the bacteria can grow with oxygen? Why some of the bacteria cannot grow with oxygen? That's related to the metabolic pathway. So, something I want to mention. During the bacterial growth, they will generate this guy, hydrogen peroxide. It's a toxication material for the bacterial cell. You have to hydrolyze using catalyst. If using catalyst become oxygen and water, this will release. This is a toxication material. Bacteria have to have catalyst to hydrolyze it. Okay. Second thing, during the metabolic process, lots of the time will generate superoxygen, like that. Superoxygen is also harmful for bacteria. You need to have something called SOD, sulfide dismutase, to break down, become this. So in order for bacteria to survive in the presence of oxygen, they must have catalyst and SOD. Without one of them, their requirements of oxygen will be changed. Now for anaerobic bacteria, why they cannot survive in the presence of oxygen? The simple reason is there is no catalyst and SOD. Because all those toxication materials, they cannot be hydrolyzed. Oxygen for them is the toxication. So that's why they will be favorable and can grow without oxygen. Based on their enzyme content, we can categorize them into different groups. So you see, obligate aerobes, they must have SOD and the catalyst. Strict anaerobes, nothing there. Okay? So that's the story behind it. So SOD is a full name, is superoxidase dismutase, catalyst is right here. Now, how are we gonna grow anaerobic bacteria in the lab? We have two choices. One thing is we can grow using a chamber. This is called an anaerobic chamber. It's very expensive. $25,000 NOS. Because you have the system there. You input with oxygen or you take out of the oxygen and you put your hands in. It's like a working station. Most of the time in the lab, we're using this jar. We call anaerobic jar. It's not really cheaper. The jar itself, $400. How we do? We put a gas diaper there. We call it a gas bag. I call it a gas diaper, like a baby diaper. We add water there. It will react it. Generate the hydrogen and the carbon dioxide. What is the hydrogen for? Because I want to create an anaerobic environment, so I need to take out all the oxygen. Obviously, will let be reacted with oxygen in the jar, generate water. And lots of the time, we have a catalyst here to let the reaction happen more quickly. Now, how do we know the oxygen is gone? I need to put some of the gas indicator. And the gas indicator is methylene blue. If the methylene blue there become colorless, which means absence of the oxygen. Okay, so that's anaerobic bacteria what we're going to grow. Last one, bacterial biofilm. So we already talked about. This is what happens in the meat processing plants all the time. So I have lots of the meat grounded. So I make a beef patties, let's say. And one day I'm really tired. I go home. I forgot cleaning the bench. On the bench surface, as long as you have a little bit of moisture, or we say some water activity, the bacteria will grow. Even in a very poor nutrition environments. The bacterial cell will connect it with each other based on the van der Waals force. And some of them will dislodge, some of them will continue there. Eventually, they will create a matrix. A matrix could be stay there for a couple of days, couple of weeks, or even years. They'll survive there in a poor nutrition status based on the cell-to-cell communication between the cells because of chlorine sensing. They can stay there. The really bad thing for the biofilm is they resistant to antimicrobials and the sanitizer. So I mentioned earlier, if we using chlorine to clean it, generally we only need 200 parts per million. For biofilm, even you using 1,000 parts per 1,000 parts per million, it's not going to kill them probably. So this is very interesting for the biofilm formation on the surface. Which microscope tools we should be using to do the observation? Laser confocal microscope, because we can see 3D images for the matrix of the bacterial cell. Okay? So this is what we have for this section. We need to continue to talk. So this section is done. We're going to go to lecture 5. Let's see what we have. Okay, we talk about bacterial media. Okay, this is the one is relatively tricky, but we could talk about something. Okay, bacteria media. Lots of things in the information, but we want to give you some of the concept. Obviously, bacterial media is for bacteria to grow. And we already talked about there is a major 2 different categories, which is liquid media and solid media. Liquid media like a Boss solution, and solid media like agar plates. And this is basically is for physics status. And we know about that. But more important, we want to talk about is the floral function status. How the bacterial media going to look like. So let's talk about these slides. Based on their chemical composition, bacterial media could talk about defined media and complex media. So what means defined media? Which means every single chemicals is defined very well. Other than that is complex media. So I give you an example. Above is a defined media. You look at that, every chemical defined very well. You know every single ingredient. But below, neutral broth, McConkey agar, and tropic soil broth, it's a complex media. Why? Because the ingredients like beef extract, like peptone, like tryptone, we don't know what's inside. It could be a bunch of the amino acids and with protein. So that's because it's a complex media. This is a little bit tricky, but not really difficult to understand. The second one is a physical nature. We have a liquid media, solid media, and semi-solid. Semi-solid media is to testing bacteria motility. We're not going to emphasize too much here. That's basically for major students because it's testing bacteria whether they have a flagella. So we want to talk a little bit about here about this function. Okay, so we want to talk about here. So based on the function of the bacteria, we could categorize as number one, support medium. So let's say nutrient broth. Or bacteria beef extract solution. Those are support medium. What this means, majority of the bacteria can survive. There's no question about it. You put the E. coli there, it will grow. You put the Listeria, it's grow. That's called support medium. Second one is called enriched medium. There are two examples for enrichment medium. Number one is blood agar. Blood agar is very important. We're going to mention about that all the time. What is blood agar? Is general agar. You add 5% sheep blood. So blood agar looks very red because we add sheep blood there. But why are we using sheep blood? Because the research has been done 40 years ago. They find the characteristics of the sheep blood and the human blood are the same. So they using 5% sheep blood. Blood agar is enrichment media, which means the bacteria can grow dramatically. So support media basically going to 10 to the power of 7 and 8. The enrichment media can go to 10 to the power of 9. Lots, huge. We wanted them to grow dramatically for clinical purpose. That's enrichment media. Enrichment media, we have another example, is chocolate agar. Okay, first of all, chocolate agar, there is no chocolate there. It's not a general medium, you put a candy ball, put a chocolate there, they manufacture become a chocolate agar. No. Lots of people think that way. No. Nobody make a media adding chocolate there. Why we call it a chocolate agar? This is a blood agar heated at 70 degrees Celsius. Then turns brownish color. Looks like a chocolate. So we say chocolate agar. So originally, chocolate agar is called chocolate-like agar. But then people think you're smart. Take this off. They become a chocolate agar. Ideally, it should be like this. Not confusing. Now, why chocolate agar is important? Because they used to grow fastidious bacteria, which means the bacteria are very picky, such as Haemophilus influenza, such as Campylobacter. So that's chocolate agar. Number three, what I want to talk about is selective media. Since it's already called selective media, what it means? Some bacteria can grow, some bacteria cannot grow. So I'll give you a very example. If I have a nutrient agar, I add 50 parts per million penicillin. This is a selective media. Because most of the bacteria will be died because I add penicillin, only penicillin resistant bacteria will grow. So that's a selective media. Last category, differentiated media. Okay, what means differentiated media? Based on biochemical reaction, we have a different color. A typical example is blood agar. Blood agar, since we have a blood cell, we could lytic of the blood cell, therefore have a different category, which means alpha hemolytic, a beta hemolytic, and gamma hemolytic. So alpha hemolytic is usually greenish color of the colony, incomplete hemolysis. Beta hemolytic, most of the time, looks like this, transparent, completely lytic blood cell. Gamma hemolytic, nothing will happen. Remember those three. Exam 2, we will talk about the human pathogen. We're going to mention about that. Okay? Now, what are the things really difficult? The difficult thing here is there are some of the bacterial media, it fits 2 or 3 of this category. That makes it confusing. So I gave you example today, then we're going to let you go. A very common bacteria to cultivation, a bacteria everybody knows is E. coli. The agar called Macanchi agar. Macanchi agar is for E. coli, growing, all type of the E. coli. First of all, it is a selective media. Why? Because it has crystal violet. So you should know, and I may not mention, E. coli is gram-negative bacteria. Crystal violet, using in the gram stain, the first step. Why gram-positive bacteria stains purple? Because it's attacking it, which means you're going to kill it. So crystal violet in the Macanchi agar, it's killed all gram-positive bacteria. Only gram-negative bacteria will grow. It's a very magic agar. Using Macanchi agar, you already categorize 50%. It's a selective media. But why it is also a differentiated media? Because of the neutral red. And Macanchi agar containing one very common sugar called lactose. And you heard about that. Some of you are lactose intolerant. What this means? You can drink milk. After drinking milk, you diarrhea, vomiting sometimes, maybe severe. That's lactose. Lactose is a disaccharide. It's glucose and galactose combined together with 1,4-glycosidic compounds. So lactose. Lactose in this medium, if bacteria using lactose, the neutral red is a pH indicator, it will showing you pink color. That's lactose fermentation positive. Otherwise, it's colorless. So lactose fermentation negative. So Macanchi agar, originally it's called lactose Macanchi, but people think you're smart. Take this off. Because there's another Macanchi agar is sorbitol Macanchi. So what is sorbitol? It's glucose going through hydrogenation becomes sorbitol. Sorbitol is a sugar alcohol. Where you can find the sugar alcohol, you never realize, but I'm better you used it. You go Starbucks. You said, I want a cup of coffee of, let's say, vanilla mocha, let's say. I find it's not sweet enough. You just say, I want a bag. They give you two types of the sugar. You will see there's a crystal there. That's really sugar. Other, you see a very small, tiny bag. That's sugar alcohol. Sorbitol is one of that. There is a theory that said sugar alcohol is good for diabetic patient. But the debate has been going on for 10 years, 20 years, maybe not. Okay, it can be disrupt your metabolic of the sugar, blood sugar. So just want to let you know, shouldn't be called lactose McConkey, because general McConkey agar have lactose, but they think you're smart, they took it out. Okay, so what McConkey agar looks like is that. First of all, if they grow gram-negative bacteria like E. coli. Second, you see the pink colony, lactose fermentation positive. They use lactose. What are the products going through fermentation? Everybody can think about it. Of course, acid. So like cheese going through fermentation, that's why cheese is a little bit acid. I mean, some of you like it, I don't like it. It's too salty. There's lots of salt there, and it's very acid. So that's the McConkey agar. Okay. All right. Blood agar, we already mentioned. McConkey agar, we're going to mention. We're going to off here. This is the slides we will mention again, and I hope you remember it. Why? It's very important in the microbiology world. This tells you a blood agar have a very important meaning for the clinical microbiology area, because it could differentiate Streptococcus pyogenes, beta hemolytic. Streptococcus pyogenes is caused strep throat. I often say this, before the COVID-19 comes, this is the most excuse. The students will tell me, you're not going to come into my class, I have a strep throat. Which pathogen? Streptococcus pyogenes. Using blood agar, we can know beta hemolytic. Second one, Streptococcus pneumoniae. Why we know it? Sometimes you coughing, sneezing, you have a fever, you go to see a doctor, they give you pneumococcal testing real quick. Another way to do real quick is on the blood agar. You see the dark green colony there? That is incomplete hemolysis, are typical alpha hemolytic results for Streptococcus pneumoniae. Okay? So that's what we have today. Then we can finish majority of these on Thursday.